Okay, good morning, guys.
Good morning.
Thank you. Oh, my Q camera isn't fired up. All right. Sorry, I have a bit of a sore throat this morning, so I'm going to be speaking a little bit less than I normally do. Today, we're going to begin on the last chunk of this class, which is on integration. But before that, a few comments on exam 2. If you missed exam 2, for whatever reason, you need to contact me. Nala, get out of there. That's not your fucking food. Sorry, one of my cats being a bitch, stealing the other cat's food. If you missed exam 2 for any reason, you need to email or Canvas message me immediately. So we can set up a makeup or something, you know. So that's definitely important. You do not want to be cruising through this test with an exam grade missing, or cruising through this class with an exam grade missing. That would be a bad idea. I'll work with you as much as I can. So whatever reason, I don't care the reason. Let me know what's going on, and I'll do my best to come up with a fair and reasonable solution. Today, I guess I should also say exam 2 will be graded on grades entered no later than this Friday. My printer is out of toner right now, so I'm waiting for some toner to come in before I can actually print and mark your free response stuff. So I have not started marking your free response questions yet, but I will be starting on that very soon, and they'll be up no later than Friday. Okay, so today, we're going to start talking about the second half of calculus. So there's a bunch of ways to kind of subdivide calculus into different topics. Is the screen share not working? It's not, is it? Yeah, okay. So if you missed exam 2 for any reason, send me a message right away. Exam 2 grades will be up no later than Friday. Today, we're going to start talking about the second half of calculus. You can subdivide calculus into kind of subgroups based on a lot of different things, but one of the most common ways to do that is to talk about differential calculus, which is what you guys have been doing so far, calculus that involves differentiation or taking derivatives, and integral calculus. So the second half from that perspective is integral calculus. But really it's two sides of the same coin, or it's walking one direction on a ladder versus the other direction on a ladder. So the integral problem can be expressed a few different ways, and I'm going to introduce it to you in terms of area, But what you're going to see eventually is that it is closely linked to the derivative problem. So finding area is somehow related to something like a derivative. And I think it's best to just start talking about it straight away. So here's the motivating question. Can we find the area under a curve so I have some function here. And I give myself two numbers, A and B. And I want to know, is there any way to come up with a formula for the area bounded by this curve and the x-axis Is there any clean way to come up with a formula for that area? At a glance, this doesn't appear to be at all related to what we've been doing. And we're going to start by solving this geometrically. We're going to do something kind of obvious. We're going to start filling that area up with rectangles. And then we're going to use some limits to make the rectangles really narrow so that the approximation that we get from those rectangles becomes very, very good. But then what we'll see is as we send that limit wherever it must in order to get the approximation very, very good, something funny involving derivatives will happen. Before I jump straight to the way we attack this, I'd like to show you an example or two where we can do the calculation exactly. So the general answer came from Bernard Riemann. Well, one of the answers came from Riemann. There were other answers before them. Can we try approximating? With rectangles. So what I mean by that is I'm going to chop this interval up into a bunch of little pieces. And then in each piece, I'm going to draw a rectangle. And the way I'm doing it here, I'm determining the height of the rectangle by the right-hand side, but we could do it the other way. So definitely make sure you're adding this picture to your notes. I think we would all agree that the total area under the curve there is pretty close to the area of these rectangles. And if I call this x0, this x1, x2, x3, x4, x5, x6, and x7, then I can come up with a formula for the area of these rectangles. Because this point right here has y value f of x1. This point has y value f of x2. This point right here, because it's on the graph of f of x, has y value f of x3, and so on. So these areas, the rectangular area, the exact area, is close to the rectangular area, which is, well, each of these heights and each of these widths need to be calculated, and then we multiply them. Well, this is the area of the first rectangle plus the second rectangle plus out to the last rectangle. In this case, that's the, let's see, we got 1, 2, 3, 4, 5, 6, 7 rectangles. So there's a few things that we're going to want to do as we start getting comfy with this. We're going to want a notation for big addition problems. We're going to want some notation for these horizontal distances. We're going to need to be comfy with where these heights are coming from. And we're going to want a general way to express the exact area. So there's going to be a meaningful amount of formula work here, I guess is what I'm saying, right? So you may remember sigma notation from your pre-calculus class, summation notation. That's the nice way to write big, long addition problems. The horizontal distance here, we usually call delta x, and we usually make these all the same. So I would usually make this like b minus a over however many rectangles I want, which would be 7. That way there's 7 rectangles, all with the equal width. And then the game is going to be, I'm going to use more and more and more rectangles. The more rectangles I use, the more accurate this approximation becomes. I've got this little piece here that hangs over, so there I'm overestimating the area. I've got this piece here which doesn't get measured at all, so I'm underestimating the area there. And if I use more and more narrower and narrower rectangles, then those error places will get smaller and smaller and smaller. So that's the basic idea. This is called a Riemann sum. So this stuff is called a Riemann sum. The exact area here is called a definite integral. So the rectangular areas, which can be expressed this way, are called Riemann sums. This thing is called the definite integral of f of x from a to b. And we have special notation for that also. So there's going to be a lot of new symbols, a lot of new notation. There's going to be a fair amount of like difficult calculation involving large sums. And then after we get comfy with this, we'll be able to develop some other ways of doing the calculation. But we have to go through this process of Riemann sums first. So I'll just take a quick look at the section in your textbook and show you how they introduce this. Where did I put that? Oh, do I not have your textbook open anymore? What? Okay, so 5. So We're just talking about the area problem here, right? And this is the sort of thing that we're going to do. We're going to be using these little rectangles to get better and better and better approximations of these areas. So they're using this notation Rn for the nth Riemann sum, the Riemann sum with n rectangles. And here are these pictures, which they can draw much better than me with computer software. So you see what I'm saying? As I use more and more rectangles, my approximation becomes better and better and better. Here they're doing the same sort of thing I did, where the height of your rectangle is determined by the value of the function at that right endpoint. And that's why you see the R here. That stands for a right Riemann sum. Over here, they're letting the height of the rectangle be determined by the value of the function at the left endpoint. And that's why you see the L here. So there's two types of Riemann sums to contend with: right-hand Riemann sums and left-hand Riemann sums. But either one will do the job as long as you use infinitely many rectangles. So you use more and more and more rectangles, and you get a better and better and better picture for the area. And there's a few other ways to do this, but we're not going to worry about midpoints or mixing left and right Riemann sums. I don't want to overwhelm you guys. I want to get to the good stuff and get there fast. So that's it, right? Okay. And then we define these in terms of those. All right. Let me double check the syllabus really quick to make sure I'm not skipping anything. I don't think we are.
So the graph you drew is using right and left hand.
So the graph I drew, I think, is just using right-hand Riemann sums.
I'm just confused because it's a different shape.
Yeah, that's it, right? So if the function is monotone, either always increasing or always decreasing, then it's easy to get a little bit confused between the right-hand Riemann sum and the left-hand Riemann sum, because one side isn't always above the other. So I don't have it on here. Oh, that's right, because it's not a part of our official curriculum. Okay, that's fine. That's fine. So there's a section that we don't officially teach at Santa Fe that I usually like to go over that introduces the concept of an antiderivative, and it's back here. So this is going to be an important concept for us as we move forwards, but for whatever reason, it's not like when you look through Santa Fe's list of sections that we cover in Calc 1, it's not there. So I'm going to recommend, let me come back to the notes. That's right, I knew there was something weird here. So first off, I want to deal with Angelica's question or comment there. This kind of looks like a combination of both pictures, right? But that's because in those pictures, the function was increasing everywhere. But you'll notice that this rectangle, his height is determined by the value at the right here. Yeah, the height of the function at the right side. And the same is true for all of these. If you ask, where does this height come from? They're all coming from the right endpoints. So even though over here we're underestimating and over here we're overestimating, they're still both right-hand Riemann sum rectangles. That's a good observation. We're going to need a crash course on antiderivatives, but I think I'm going to shove that in when we get into section 5.2. So a quick note. I suggest reading. I remember being surprised by this. Section 4.9 to introduce the idea of an antiderivative. I will go through that this week. We're going to talk about the area stuff from the geometric perspective first, but then when we come to the calculus perspective, we're going to need the concept of an antiderivative. Okay, so notation. If I want to add up a bunch of things, if I want to express a big addition problem, which follows a nice pattern, compactly, I can use what's called sigma or summation notation. This is something that you're supposed to discuss in MAC 1140 or 1147, but I know not everybody gets to, so we're going to go over it really quickly. So here it is. If I wanted to express the sum 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, what I notice here is that I'm adding up 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. The numbers downstairs are consecutive, right? 3 comes after 2, 4 comes after 3, 5 comes after 4, and I've got everybody between 2 and 6 here. So I could say this looks like I'm adding up 1/n from n equals 2 to n equals 6. And there's a special notation for this. The notation is capital sigma, that's the Greek letter sigma, 1/n, and then you put from n equals 2 to n equals 6 over here. So the thing you're adding up goes over here. The range over which you are adding those things up go on the bottom for the start and on the top for the end. And then you've got this capital Greek sigma here. That's the Greek S, standing for sum or summation. I'll do one more where we go the other way. I'll give you the summation notation. And this guy I would like to unpack. So this guy says you're adding up these things from n equals 0 to n equals 5. So that's going to be 2 to the 0 plus, I have to go all the way from 0 to 5. So the next guy is going to be 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4 plus 2 to the 5. I don't know how much of this you guys have seen in the past, so I would like to use the little react options here in Zoom. If you have seen sigma summation notation before, go ahead and give me a thumbs up. Okay, so most of us, but not all of us. All right. So the next question is, how do I write the Riemann sums in the sigma summation notation? So I'm going to redraw that picture I had there, here. only with the assumption that rather than using 7 rectangles, I'm going to have n rectangles. So I'm going to chop the interval AB into capital N equal length subintervals of, we'll talk about what each one's length will be in a minute. So here would be that first subinterval and that first rectangle. And the second subinterval and the second rectangle. But I'm going to put some dots in here to say, well, I'm going to allow n to be, capital N here to be like a variable. So I don't want to draw the picture to have a specific number of rectangles, but there will be like an arbitrary one in here, or a generic one in here, which I'm going to call the ith rectangle. And then I'll have my last one over here. And there'll be some more like dots. Okay. So just like before, A, I will call x0. This guy I would call x1. This guy I would call x2. This guy I'm going to call xi minus 1. And this guy I'm going to call xi, because I don't know how many rectangles there are in between there. As the picture is scaled, it looks like there's only room for one, but I want to imagine there being a shitload of rectangles, an arbitrary number of rectangles in there. B, I will call xn. And so the one right before him would be xn minus 1. Each of these subintervals, so here's where we're going to start getting a little bit technical. Each subinterval, each of these widths is of length well, if I have n of them all together and the total length is b minus a, then the length is b minus a over n. And we call this delta x, because I'm chopping something that has length b minus a into n equal length pieces. The total length of this interval is b minus a, and if I want to chop that up into n pieces, each having the same length, then each piece has length b minus a over n. So this horizontal distance is delta x. This horizontal distance is delta x. Every rectangle in between those has horizontal distance delta x. This guy is delta x. This guy is delta x. That's convenient because it lets me use rectangles that are all the same width, which makes my calculations a little bit easier. This point right here, his x-coordinate is xi. That's the x value down here. What's the y-coordinate?
Is it f of xi?
Yeah, exactly, right? Because it's on the graph of f of x, and the x coordinate is xi. So it has to be f of xi. So your delta x here, this is the width of each rectangle. And f of xi is the height of the ith rectangle. So then the area of the ith rectangle I'll call that AI is the height times the width. It's f of xi times delta x. So this gets me to a place where I can start writing down the area in terms of a summation. So this first guy, I would call him A1. The second guy's area, I would call that A2. And then I've got a bunch more in between here. I get to the ith one. This is what I'm going to use to come up with my general formula. The last guy, I would say, has area AN. So if I wanted to say what the full Riemann sum looks like, zoom out just a little bit here.
Is that x to the n plus 1? Right
This
before
last
b?
guy, so I would be careful with the language here. We're using a subscript. So I wouldn't say it's x to the, it's down here instead of up there. So I would say it's just x sub, and then the subscript here is n minus 1.
N minus 1. Okay, thank
Yeah,
you.
because it's the one that comes right before xn. So the subscripts go up as you go over. So the one to the left of xn should be xn minus 1. The one to the left of xi should be xi minus 1, and so on. Okay, so let's come back out a little bit. Remember what my goal is. I want to express the Riemann sum, and I'm just worrying about right-hand Riemann sums in terms of this summation notation. So I needed some way to express these areas. So Rn, this is A1 plus A2 plus the middle terms there look like AI, and then all the way out to AN. This is what I get when I add up all of my little areas. I could write that as sigma I from 1 to n of AI. This is just rewriting this big addition problem in the summation notation. Because what am I doing here? I'm adding up all of the A's, A1 plus A2 plus A3 plus A4, all the way out until I get to AN. So that's sigma I from 1 to n, AI. Add up this stuff over this range. But then I have a formula for AI. AI has to be f of xi, the height, times delta x. So we can sneak this in over here. AI is the height, which is f of xi times delta x. This is the height. This is the width. And the area of a rectangle is, always its length or height times its width. Make sure we can see that, yeah. So then this Riemann sum, the formula for this Riemann sum, I know what these AIs are. I can just plug that in. So I get the sum from I equals 1 to n of f of xi times delta x. Right, like this. And then the observation, the crucial observation here is that as n goes to infinity, as capital N goes to infinity, the approximation becomes exact. So the exact area under f of x from x equals a to x equals b, and this is a definition. We don't need to use that notation. That area is equal to the limit as capital N goes to infinity of Rn, which is the limit as capital N goes to infinity of sigma I from 1 to capital N f of xi times delta x. And this is the game. So the thing I want, the exact area under my curve, is the limit of the Riemann sum. And the Riemann sum I now have a formula for. So this big scary looking expression is the thing that your friends, after they took Calc 1, all told you, holy shit, fuck this part of the class, I hate this stuff. The Riemann sums, this is it, all right? This is the thing that everybody hates. Good news, I'm not gonna make you do a lot of these calculations. Bad news, I'm gonna make you do some of these calculations. So I can't, in good conscience, let you guys finish Calc 1 without making you do 1 or 2 explicit Riemann sum calculations. But very quickly, we're going to move from here to 5.2, where we'll start using calculus and antiderivatives to do this. There is a notation for this exact area. This guy. This is called the definite integral of f of x from x equals a to x equals b. And another way of saying that is with this big long S symbol. And you've probably seen this if you look through your textbook or elsewhere, with an a down here and a b up here and f of x dx, like that. You don't need this for the section we're talking about today, but I figured we're here, I might as well show you. And there's some notational similarities between this and this, right? You've got like an f of x and a dx here. You've got like an f of xi and a delta x here. You've got a big capital Greek S here. You've got a big Latin S here, right? This integral symbol that you've seen in your textbook, it's just a stretched out S, and it stands for summation the same way that the Greek one stands for summation. It's just a different kind of sum. But for us in this section, in section 5.1, this is what we're concerned with, right? This. So this is the thing that I need you guys to commit to memory for the purposes of today's lesson. And you need to also remember that delta x is B minus A over capital N. So I'm going to return to the textbook for those pictures again. Hopefully not.
Can you pull that definition up for one more second? Thank you.
Yeah, sure.
All right, it's all good now. Thank you.
Right. So what we have here is a purely geometric attack for finding areas. Right here, what they're trying to illustrate is n going to infinity in Rn. The exact area is the limit as n goes to infinity of Rn. And you could use Ln also, but we won't bother with that. So here, as I use more and more rectangles, remember n is the number of rectangles. So if I use 10 rectangles, I get an okay approximation for the area. If I use 30 rectangles, it's getting closer. They say that the exact area they know ahead of time is 1/3. And if I use 50 rectangles, I'm getting really close, 0.3434. That's really, really close to 1/3. So as n, the number of rectangles, goes to infinity, this becomes exact. So what we need to do now is get to a place where we can calculate all of these heights and all of these widths, and then add them all up. The hard part is in the addition. So here it is, right? The total area is the limit of Rn, which is the limit of this Riemann sum. And here they've written the Riemann sum out in the ... notation instead of the sigma notation. The next little bits in here, they're talking about other ways to cook up Riemann sums. You can talk about upper and lower sums. There are things called Darboux sums. They've got a brief explanation of sigma notation. But the way to get to a place where you can do these calculations, you need to remember some of these formulas from your pre-calculus class. So like the sum of the first n squares, 1 squared plus 2 squared plus 3 squared plus 4 squared, etc. You got to get to a place where you can do that. So I'm going to run through a few of these calculations with you. And then we will talk about how to do the exact calculations using calculus. Okay. So let's construct I should come back here, sorry. Let me add one other thing here. What we don't have in this on this page is a formula for the xi's, right? You can get them from the picture, but I should tell you that depending on what a and b are, xi will change. So xi is a plus, where's my picture here? So x0 is a, x1 is a plus one of these widths. That's a plus one copy of delta x. x2 is a plus 1, 2 of these widths. So x2 is a plus 1 delta x plus 1 delta x is a plus 2 delta x. And in general, xi is a plus I copies of delta x. So you need this in your definition there as well. So once we have that, now we can jump in and start doing some calculation. So everybody has this written down, this box statement and these two things? Once we have this, I'm going to calculate two different areas for you exactly.
What are we using the xi equals a plus I delta x for?
So remember this, the height in here is f of xi.
Right.
Xi. How do I know what to plug into f? To
True.
get heights. So I need a formula for the xi's. So that's all. So the way we go through these calculations, First, you draw the picture, right? You graph the function f on the interval a, b. Then you calculate delta x. Then you calculate xi. Then you plug those things in to this formula. Then you cook up that sum using stuff from your pre-calc class, which I'll review for you as we need it. And then you take the limit as n goes to infinity. So you build this object from the inside out. First you calculate this, then you calculate this, then you add the sum in, you calculate that, then you take the limit. So let's do it. The first one is that I want to do for you is one that we could cook up without any calculus, including limits. I'm going to find the area under f of x equals 2x from x equals 0 to x equals 3. So I'm going to start by drawing the picture. F of x equals 2x, that's a line with slope 2 going through the origin. So I'm going to call this 3. And that means this height up here is 6 because the slope here is 2. So here's the area I'm after. And what you notice is that that's a triangle, right? The height is 6, the base is 3. So we know that the exact area is which is a triangle, because this is a linear function, has to be 1/2 base times height, which is 1/2, the base is 3, and the height is 6. So this is 9. But now I'm going to get there using my Riemann sums. A is 0, B is 3. So can we do this with Riemann sums? First, I need delta x. That's always b minus a over n, which is 3 minus 0 over n, which is 3 over n. And then I need to think about my xi's. That's a plus I delta x. A is 0. I is I. And delta x is 3 over n. So this is 3i over n. So now Rn is the sum from I equals 1 to n, f of xi times delta x. I know what delta x is, so I can plug that in. That's 3 over n. I know what xi is. That's 3i over n. So this is sigma I from 1 to n of f of xi is 3i over n times delta x, which is just 3 over n. But what is the function f? What is this piece? F of anything is 2 times that thing. That's all. So f of 3i over n is 2 times 3i over n. So this is sigma I from 1 to n, 2 times 3i over n times 3 over n. And this is where your familiarity with the sigma summation notation becomes crucial. So if you haven't played with this stuff in a while, or God forbid, you didn't get to play with this at all in pre-calculus, we need to remind ourselves how this sigma operator works. And the easiest way to remind yourself how this thing works is just remember that it's a big addition problem. So you can factor constants out. You can split it up over addition and subtraction. You cannot split it up over multiplication or division. So first I'm going to put everything in there together, combine all my like terms. I get sigma I from 1 to n. Sorry, I have a tendency to draw my sigmas with a small little bloop in the middle there. I've got 2 times 3i times 3 upstairs. So that is 9 times 2 is 18i upstairs. And just n downstairs. And now I'm going to write this out because it's the first time we've done it. In general, you won't write these out. You'll just pop out the things you can pop out. But I'm going to try to justify to those of you who haven't seen sigma notation in a while why I can do this. Remember what this says. This means add up all of these things from I equals 1 to n. So this is 18 times 1 over n plus 18 times 2 over n plus 18 times 3 over n, all the way out till the last term here is 18 times n over n. Is everybody comfy with why this is the same as this? I'm just writing out the sum that this encodes. I'm summing from I equals 1 to capital N. So that means I'm going to replace this piece by the numbers 1, 2, 3, 4, all the way up to capital N. And then I'm going to add up this thing over that range. So here's the I equals 1 term, plus here's the I equals 2 term, plus here's the I equals 3 term, plus all the way out till we get to the I equals n term. I can factor an 18 from the top and an n from the bottom. So this is the same as 18 over n times, what's left here is just 1 from this guy, 2 from this guy, 3 from this guy, all the way out to capital N from the last guy. In other words, this is the same as 18 over n times the sum from I equals 1 to n of I. And normally I would jump straight from this statement to this statement, saying, oh, well, this doesn't have any i's in it, the 18, and this doesn't have any i's in it, the n. So with respect to the sum, 18 over n is constant, so I can pull 18 over n out. And what's left inside is just I over 1, or I. So normally I would jump straight from this statement to this statement. And here I'm doing these in-between steps where I write things out to help you see why that shit works. So here's the 18 over n factored out. And then what's left in the brackets here, this is the sum from I equals 1 to n of I. So what I need in order to simplify this and then take a limit, I need to know what this sum is. I need to know what this sum is right here. This piece, which is this piece. What happens if you add up the first n integers? Does anybody know? Does anybody remember how to add the first n integers? There's a really cute story behind this. I don't know if I have time for the story, but. Okay, what if I take the first and last term and I add them? I'll have n plus 1. If I come back 1, I would have n minus 1, and if I come over here 1 plus 2. And then I came in 1, I would have n minus 2 plus 3. If I add from the outsides coming in, I get n copies, or I get n over 2 copies of n plus 1. So this is the same. I'll bring my 18 over n down here. this sigma piece, or if you like the expanded version here, is the same as n over 2 copies of n plus 1, or n times n plus 1 over 2. So this is 18 over n. Did I do this right? 18 over n. Did I have another n somewhere? Oh, I'm so sorry. This is an n squared. Yeah, we had a 3 over n. So I need to apologize. Back at this step, we had 2 times 3 times I times 3 upstairs. That's 18i. But then downstairs, I had n times n. So these are all n squareds downstairs. So this is an n squared. This is an n squared. This is an n squared. Yeah, please take a second and fix that. I'm sorry. So I'll go ahead and write this with the formula plugged in. N times n plus 1 over 2. Okay. So yeah, so these two n's downstairs we're multiplying, so we get an n squared downstairs. So just come back here, n squared, each of these, n squared. So we're not factoring 18 over n out, we're factoring 18 over n squared out. So this is an 18 over n squared, 18 over n squared. So this piece is 18 over n squared times n plus 1 over 2. So now we're almost there. Remember, my exact area is the limit as n goes to infinity of the Rn's. And now that I have a nice formula for the Rn's with no dot dot dots and no sigmas, I can try to take that limit. So the exact area under f of x equals 2x from x equals 0 to x equals 3, that's equal to the limit as n goes to infinity of the Rn's, which is the limit as n goes to infinity of 18 over n squared times n plus 1 over 2. And if I can calculate this limit, I win. And we've seen limits at infinity before. We know how to do this stuff. So let me distribute everything in the top and distribute everything in the bottom. This is equal to the limit as n goes to infinity, 18 times, this is n squared plus n upstairs. And downstairs I have 2 times n squared. So that's lim n to infinity, 18 n squared plus 18 n over 2 n squared. And we've seen limits like this back in section 2.6. This is going to be 18 over 2, or 9, which is what we found earlier using just geometry. Right? So if you were to divide top and bottom in this expression by n squared, that's how we did it back in section 2.6. This would become 18 plus 18 over n divided by 2. So the 18 over n would go to 0, and you just get 18 over 2. Or if you like, you can take the ratio of lead coefficients. I think that's how most people end up doing that in their head. But in either case, we get 9. So the exact area underneath that curve can be calculated through this Riemann sum thing. And we get the same thing we did here. I think the difficult steps are understanding what to do with this thing, realizing that this thing is the same as this thing. So if a piece here doesn't have any i's in it, you can factor it out. Because that's what we did here, right? We had all of these things, and there are these common terms. Every term has an 18, so I can factor an 18 out. Every term has n squared downstairs, so I can factor 1 over n squared out. And what was left is just the stuff that didn't have that. So from the first term, I had the 1. From the second term, I had the 2. From the third term, I had the 3, and so on. The other challenging piece is once you get it down to something like this, you have to know what the hell to do with this thing. And this is something that you have to remember from pre-calculus. So I'm going to give you a few formulas for sums like these that you will need to calculate all of these Riemann sums. We won't be able to calculate any Riemann sum exactly, only the ones that simplify to something nice and simple like this. Because that's what allows me to get rid of the capital sigma, knowing that this piece is equal to this piece. So I'm going to give you some formulas.
Sorry.
I'll leave this here for now. I'll start with the formulas down here. So summation formulas, needed, necessary summation formulas. So the proper plural of formula is formulae. So I'll say it like that. If you add up I from 1 to n of just I, this is the one we used here, you get n times n plus 1 over 2. And this is the one that has that cute story behind it involving a little childhood Gauss. If you add up the first n squares, you get something very similar to this. You get n times n plus 1 times 2n plus 1 all over 6. And if you add up the first n cubes, I want to double check myself on this one because I haven't used it in a while. I think you get the square of this. But let me double check really quick because I don't want to tell you something wrong. Oh, the first n cubes. Yeah, it is. Okay, good. So these you will need when we go to compute Riemann sums, because your goal is going to be to get your Riemann sum into some stuff times one of these, and then you'll replace whatever these guys are by their equivalents, and that will get you to a spot where you can take limits. So I would like to do one more example, and I think we have time for just one more. Let's find the area under f of x equals x squared from x equals 0 to x equals 1. This is a classic problem. The Greeks worked on this but never got it. We know what f of x equals x squared looks like. It's this parabola. And if I call this 1, then the area I'm looking for here is this. So this one I cannot use geometry for. I need the calculus because the area here is bounded by this curvy thing. And curvy things make area problems wicked hard because I can't think of this as like a triangle or anything like that. It's not because of the curve. But I can still do my Riemann sum thing. So I calculate delta x. That's always b minus a over n. So that's 1 minus 0 over n, or just 1 over n. I calculate xi. That's always a plus I times delta x, which is 0 plus I times 1 over n, or just I over n. And now I construct the sum. So Rn is the sum from I equals 1 to capital N of f of xi times delta x, which is the sum from I equals 1 to n. F of anything is that thing squared, because f of x is x squared. So f of xi is xi squared. That's I over n all squared. And then delta x is 1 over n. So I'll continue this over here. This is equal to the sum from I equals 1 to n of I over n all squared is I squared over n squared. And then I still have my 1 over n. So this is sigma I equals 1 to n, I squared over n cubed. I can write this as sigma I from 1 to n of 1 over n cubed times I squared. And since this piece doesn't have any i's in it, he is a constant with respect to the sum. So he can pop out. So this is 1 over n cubed times sigma I from 1 to n of I squared. So I want to take a second and answer any questions having to do with this manipulation, because I know not everybody is comfy with summation notation, and I did not do the in-between step here of writing it all out in the dot dot dots. Are we comfy to here? Do we see where everything here is coming from? Or any questions about how we get to this point? So my I over n squared, that's f of xi. And when you square I over n, that's I squared over n squared. And then this piece is just coming along for the ride. Now I multiply these fractions straight across. I squared times 1 is I squared. N squared times n is n cubed, and everything else stays the same.
How do we know
Yeah.
f of xi is I over n squared? Is it because of the shape of the graph?
Well, it's two things. So xi is I over n. That comes from my formula.
Oh, I see.
F of x is x squared. So I'm plugging this in here. So f of anything is what you get when you plug that thing in for x, right? Like f of 2 is 4 because 2 squared is 4. F of 3 is 9 because 3 squared is 9. F of some shit is that shit squared because the function is x squared. So I'm plugging this in for x here. So if you like, the justification for that is f of xi is xi squared, which is I over n squared, because f of x is x squared, like that.
And that's why we work backwards.
Yeah, that's the idea.
Okay, thanks.
So that gets me to here, right? I square I over n, I multiply it by 1 over n, and I get I squared over n cubed. And now my goal is to factor anything out from this series that I can. So I have to ask, what can be factored out? And the answer is always, well, you can factor out any constant multiple. So what is a constant here? This series, this sum, is being done as I goes from 1 to n. So I'm replacing I by 1. So this is 1 squared over n cubed plus 2 squared over n cubed plus 3 squared over n cubed plus 4 squared over n cubed. I'll write it out one more time. So this guy is 1 squared over n cubed plus 2 squared over n cubed plus 3 squared over n cubed out to n squared over n cubed. So I can factor 1 over n cubed out, and what's left is 1 squared plus 2 squared plus 3 squared out to n squared. So these steps, if you don't want to write them in terms of capital sigma, look like this. So I'm just factoring the 1 over n cubed term now. And then this 1 over n cubed would be this 1 over n cubed. And this bracketed statement can be written in sigma notation like this. It's 1 squared plus 2 squared plus 3 squared all the way out to n squared. That's the sum from I equals 1 to n of I squared. That's this. And then I have a formula for this guy. I have a formula for this stuff. The sum of the first n squares is n times n plus 1 times 2n plus 1 over 6. So Rn is equal to 1 over n cubed times sigma I from 1 to n I squared, which is 1 over n cubed times n plus 1 times 2n plus 1 over 6. Where I make use of the formula that I gave you, the summation formula here. All right, I can zoom out a little bit if you want. So I'm using this formula here to replace this piece by this piece here. So now what I want to do is I want to send n to infinity in this expression. So I want to simplify this as much as I can and then take the limit as n goes to infinity. So I'll multiply everything out. That's n squared plus n times 2n plus 1 2n plus 1 all over 6n cubed. And if I multiply n squared plus n times 2n plus 1, I'll get 2n cubed, that's my firsts, plus 2n squared plus n squared plus n all over 6n cubed. And if I combine my like terms upstairs, I get 2n cubed plus 3n squared plus n all over 6n cubed. So that is what Rn simplifies to. Rn simplifies to this. We could factor in n from the top and bottom and cancel if we wanted to. I won't, I'll just leave it like that, that's fine. So now we're almost ready to finish. So therefore, the exact area under f of x equals x squared from x equals 0 to x equals 1, this is the limit as n goes to infinity of Rn, which is the limit as n goes to infinity of 2n cubed plus 3n squared plus n over 6n cubed. And the way we calculate a limit like this, you can divide top and bottom by n cubed, the largest power of n. In case you don't remember from 2.6. That would give you 2 plus 3 times 1 over n plus 1 over n squared, all divided by 6 times 1, right? Yeah, just 6. Now as n goes to infinity, this piece goes to 0, this piece goes to 0, so you just get 2 over 6 or 1/3. So a lot of people would say the degree of the top is 3, the degree of the bottom is 3, so the limit is the ratio of lead coefficients 2 over 6, which is 1/3. If you don't remember where that comes from, you can always divide top and bottom by the largest power of n. So this piece would go to 0 because 1 over n goes to 0. This piece would go to 0 because 1 over n squared goes to 0. So the top is just 2 and the bottom is just 6. So the area underneath that parabola from 0 to 1 is exactly 1/3. And this is how we find areas. This is how we start solving the area problem. So your first bit of homework this week is going to come from this section. I'll have you doing calculations like this. Sometimes you will need to go all the way to the end, like we did on these two, where you send n to infinity in Rn. Sometimes I'll just ask you to find the formula for Rn, and I won't bother asking you to take the limit, because sometimes these limits are hard, because sometimes we don't have a formula like this to replace this piece. So sometimes I'll say, once you get to here, you can stop. But if you're asked for the exact area, you will need to plug in the appropriate formula for this, and then take the limit as n goes to infinity. So this is section 5.1 on areas. And yeah, if you want old homework extended, just submit an extension request. I'm still happy to do that. Class time is just about over here. So I'll say if you haven't submitted study guide 2, please go ahead and do that. I won't be taking any points off, and I'll get those study guides graded as soon as I can. So I want to get your exams graded first. So I'll be making those my priority, but then I'll go through and plug in the grades for the study guide. As long as you finish the study guide, you're going to get full credit for it. So don't panic about those, please. They're never meant to hurt you. The purpose of the study guide is just to get you to work some problems before the test. So don't panic about those grades. If you're nervous, you can plug in what if grades with, you know, full credit as long as you did them. You'll be good. Exam scores will be out no later than this Friday. And yeah, if you need any old homework extended, I'm happy to extend it. Just submit an extension request. Questions on this last example here before we scoot? I know this stuff looks scary the first few times you see it. So remember, you always calculate delta x first, then you calculate xi, then you write down this formula and plug things in. You plug in for delta x, you plug in for xi. To figure out what f of xi is, you look back at the function f and you plug in whatever you had for xi. So f of xi here is xi squared, which is I over n all squared. Then you need to do some simplification inside your capital sigma and factor out any constants. And remember, for this capital sigma, anything that doesn't have an I in it is constant because we're adding up over these I values. So constants like numbers, 2, 5, 6, 7, but also capital N stuff is constant with respect to this sum. And if you're having a hard time seeing it, you can always write it out in the long form notation without capital sigmas. Once you get to this point, you need to replace whatever's left in your capital sigma with his appropriate summation formula. And those 3 that I gave you will be sufficient for your homework. Then you can call it quits, unless you want the exact area. If you want to approximate the area with 10 rectangles, you would plug in n equals 10. If you want to approximate the area with 3 rectangles, you would plug in n equals 3. If you want the exact area, you need infinitely many rectangles, which means you need to take the limit as n goes to infinity. And there you'll have to fall back on the stuff you learned in section 2.6, where we talked about limits at infinity. So you might want to review your sigma summation notation stuff from pre-calculus, and you might want to review your limits at infinity stuff from section 2.6 earlier this summer. But that's really all you need to get through section 5.1. It's not too bad. On Wednesday, we're going to talk about other ways to write this. So that big long S thing, the curly S, we're going to start talking about that, the definite integral. Because there's a way to avoid all this shit, but it involves antiderivatives, which are hard. So there's no getting away from doing some work, right? There's no free lunch in mathematics. Either you have to grind out the Riemann sums, or you have to solve some equivalently hard calculus problem involving antiderivatives. And we will talk about those on Wednesday. I'll do some more examples of this, then we'll talk about those on Wednesday. All right? So that is all I have for you guys today. I hope you have a lovely rest of your afternoon. Watch for the new homework to drop. It'll be dropping a little bit later today. And please get started on that right away. If you need more time on any of the old homeworks, of course, just submit an extension request and I will get right on it. All right? Okay, that is it. I hope you guys, again, have a lovely rest of your day. If you need to talk more, you can also come by office hours from 1 to 2.
Thank you.
Bye, guys.